In this video, I'll discuss the capacity of the binary symmetric channel, and we'll see how to design codes that approach capacity. Recall that the channel coding problem is the following. We have a sequence of k bits, which we call the message. So it's a sequence of k bits that we want to send from the transmitter to the receiver. The transmitter first encodes mk into a code word xn. So it converts a sequence of k bits to a sequence of n bits, where n is typically larger than k. And the sequence of n bits is transmitted across the channel, which in this case is the binary symmetric channel with crossover probability p. The receiver sees yn, this is the received sequence, and then decodes it to get an estimate of mk. This estimate is denoted mk hat. So the binary symmetric channel, as we've seen previously, can be expressed, of course, through its channel transition probability, but a more useful way to look at the BSC is that we can represent yn as xn bitwise XORed with en, where each ei is IID Bernoulli P. Right. So it is this additive channel, except that the addition is not over the integers or the set of reals, but this addition is in some sense over the binary, a set of binary numbers. As we've seen in class, the capacity of the binary symmetric channel, or the maximum rate at which we can communicate across the BSCP, is equal to 1 minus the binary entropy of P. In this lecture, we'll see why the capacity is 1 minus h of p, and in particular, we'll see how to choose codes such that they operate at rate close to the capacity, close to 1 minus h of p, and can still achieve a vanishingly small probability of error. Now, what we will do in this particular video is that I won't give you a constructive approach. So I'll say all I will show is that there exist codes of rate close to 1 minus h of p and have vanishingly small probability of error. These in particular will not be efficiently encodable or decodable. Our only goal in this lecture is to see how one can even approach the capacity of the binary symmetric channel. This approach is rather geometric, so it gives us intuition as to what a good code should satisfy. Now note that to specify a code, I need to specify both the encoder and the decoder. And the encoder, which is this function f, can be implemented in various ways. And the simplest way, at least conceptually simplest way to implement an encoder is through a table. So you list down all possible message sequences, the all zero sequence, all zeros followed by 1, and then all the way up to the all one sequence. And corresponding to each of these sequences, you have the code word, which I'll denote xn of 0, xn of 1, all the way up to xn of 2 to the k minus 1. So xn of I will denote the ith code word. Now if I list them in increasing order, I can consider of these message sequences as sequences of k bits, all the way from the all 0 sequence to the all 1 sequence. But at least for easy notation, I will represent these as numbers. Number 0, 1, 2, all the way up to 2 to the k minus 1. So there are 2 to the k possible message sequences, and I will just list them in order, and the 0th sequence is the all 0 sequence, the 2 to the k minus 1th sequence is the all 1 sequence. So all these sequences are essentially stored in a table, both the sequence and the code words, the corresponding code words. Note that storing the sequences, storing mk's is not really important. It's sufficient to just store xn of 0, xn of 1, all the way up to xn of 2 to the k minus 1 in order. Right? So this is this table is known both at the transmitter and the receiver. Now the set of all possible code words xn of 0 all the way up to xn of 2 to the k minus 1 is called the code book, which I will denote by this symbol C. So the set of all code words is what I call the code book. So this is the encoder. This is how I'm going to implement the encoder. Now I haven't told you how I'm choosing the code words xn of 0, xn of 1 and so on, but once we have fixed a possible code book, this is how we are going to implement encoding. Now what does the decoder do? For the decoder, there are a number of possibilities that, number of options that one can use. Here are some commonly used decoders. So the first is the so-called maximum a posteriori probability decoder. So this does the following. So the estimate mk hat, so the receiver gets yn and has to choose a suitable mk hat. Right, so the mk hat is chosen so as to maximize p xn given yn. Right, so basically it chooses the argmax of xn of mk hat given yn. So given the received sequence yn, it chooses that message sequence which is the most likely, or in other words, it maximizes the a posteriori probability of xn having seen yn. So this is the map decoder, and if we want to minimize the probability of error, then this is indeed the best possible decoder that we can use. A similar so if all the message sequences are equally likely, then this turns out to be equivalent to what is called maximum likelihood decoding. The maximum likelihood decoder does the following. It is the argmax over all possible mk hat of pyn given xn of yn given xn hat of mk hat. Right? So note that in map decoding we are maximizing pxn given yn, whereas in ML decoding, maximum likelihood decoding, we are maximizing pyn given xn. So we are choosing that xn which maximizes pyn given xn. Now in many cases it's more useful to choose the maximum likelihood decoder over the map decoder for two reasons. One is that sometimes you may not know the distribution of xn, but of course you always know the distribution pyn given xn. In such a scenario, it's easier to compute pyn given xn than pxn given yn. Secondly, if xn is uniformly distributed, then using Bayes' rule, it's easy to show that the maximum a posteriori decoding is the same as maximum likelihood decoding. In the special case where we're choosing a binary symmetric channel or even an AWGN channel, maximum likelihood decoding turns out to be equivalent to what is called minimum distance decoding. And the minimum distance decoding is nice because it has a very geometric flavor to it. Now, all of these, the maximum likelihood decoder and the maximum a posteriori probability decoder, these are of course well-defined quantities, but you basically look at probabilities and it is geometrically harder to see what is really happening. On the other hand, what the maximum likelihood decoder does is the following. So you have a distance function and you choose the message or the code word which minimizes the distance Right? So it's some distance between the received sequence and the code word, right? So one way to view this is the following. So suppose, of course, I'm drawing a rectangle, but consider this to be the space of all possible received sequences and the space of all possible code words. Now, when we are talking about the binary symmetric channel, then the space of this space is basically 0, 1 to the n, right? Set of all possible binary sequences. Some of these are code words, right? And any of these code words might have been transmitted. You receive a particular sequence. Let us say that this particular sequence has been received. What the minimum distance decoder does is the following. So you consider some distance and then find the distance of this point to every possible code word. Right? Find the distance to this code word, find the distance to this code word, and so on. So you find the distance to every code word and choose the code word which minimizes the distance. So basically what you're doing is, given the received sequence, you choose the code word which is closest to the received sequence. So in this particular case, let us say that this is the closest sequence, then the minimum distance decoder basically outputs this particular code word. Now for this we need a distance metric, and for the binary symmetric channel we use the following distance metric. So it's called the Hamming distance. So the Hamming distance between two binary sequences is the number of locations in which the two sequences differ. So for example, if you consider the sequences 0 1 0 1 0 and 0 0 0 1 0, then these two sequences differ in one location, so the Hamming distance between these two is 1. Okay, so this is what is called a minimum distance decoder. For the AWGN channel, we also use a minimum distance decoder, but instead of the Hamming distance, we use the standard Euclidean distance. But geometrically it is the same. So given the received sequence, you output the code word which is closest to the received sequence. Now, sometimes analyzing the minimum distance decoder is difficult. So instead of the minimum distance decoder, we use what is called a bounded distance decoder. And basically what we do is the following. Now in the minimum distance decoder, you have to compute the distances to all possible sequences, and then you output that sequence which is the closest. The bounded distance decoder instead does the following. Given the received sequence, you have a bound of r. So the bounded distance decoder specified by a parameter r does the following. Given the received sequence, you look at all possible sequences which are at a distance of at most r. If there is only one sequence of distance at most r, only one code word which is at a distance r from the received sequence, then you output that as the transmitted code word. If there is no sequence, or if there are more than one sequence within a distance r, then you output an error. So mk hat is the following. So mk hat is equal to mk hat if the distance between the received sequence and the code word corresponding to mk hat, so if this is less than or equal to r, and all other code words is greater than R. Right? So this is mk hat. Now if there are multiple sequences or if there is no sequence within a distance R, then it outputs a generic symbol which is error. It just gives up. Okay, so suppose that this is the received sequence and these are possible code words. This is the code book. The black dots denote the code book and the green dot denotes the received sequence. Now in this case there is only one sequence which is within a distance of R from the received sequence, so it outputs this particular code word. Now if there are multiple sequences, so suppose that this is the received sequence, then and you look at all possible sequences within distance R from it. If there are multiple sequences, then it outputs error. At the same time, if say this sequence is received and there are no code words within a distance R from it, then again you output an error. So this is called a bounded distance decoder because you only look at all sequences within a bound of R and then output only if there is a unique sequence within that bounded distance. So in this lecture we'll analyze the bounded distance decoder for a certain codebook for the binary symmetric channel. So now that we have specified a codebook and a decoding rule, what can we say about the probability of error? Now even in the probability of error, there are two possible choices for how we measure the probability of error. One commonly used metric is the so-called average probability of error, which is the probability of error averaged over all possible message sequences. So suppose that you transmit a message mk across the channel, then the probability of error conditioned on mk being transmitted is this particular quantity. So this is the probability of error given that mk was transmitted. Right? And this is the probability that g of yn is not equal to mk given that mk was transmitted. Right? So this is for a given message sequence and you average over all possible message sequences. So one can want the average probability of error to be small, and in many applications this is good enough. Sometimes we have a more stringent requirement on the probability of error and we instead go for the maximum probability of error. So the maximum probability of error is defined as the maximum over all possible message sequences of the probability of error given that mk was transmitted. Right? So this is the average versus this is the max. Now the probability of the max probability of error being small ensures that no matter which message we transmit, the decoder makes an error with a very small probability. On the other hand, if the average probability of error is small, then we can say that for most message sequences the probability of error is small. It is possible that for some messages the probability of error is large, but for most other messages the probability of error must necessarily be small. It turns out that although these are two different metrics, the average probability of error and the maximum probability of error, the capacity of any discrete memoryless channel remains the same. So the DMC, the capacity of a DMC with average probability of error turns out to be the same as the capacity of a DMC with max probability of error. So since this is the case, we will analyze the performance of codes with average probability of error. All we want is that the rate should be as large as possible and the average probability of error should be vanishing with n. So now we have a clear cut. So I already told you how we are doing encoding, how we are doing decoding. Specifically, we will analyze bounded distance decoder, and we've seen what is the probability of error that we're using. Right now, we will analyze the performance of the code with respect to the bounded distance decoder, and note that the bounded distance decoder is not optimal. In particular, the performance of if you want to minimize the probability of error, then you should really be using the map decoder. For BSCs with uniform inputs, the map decoding is equivalent to the ML decoding, which is also equivalent to minimum distance decoding, but this is not equivalent to bounded distance decoding. So in general, bounded distance decoder will give a probability of error which is larger than that of the minimum distance decoder. But in this lecture, all I want to do is show that there exists a code which achieves a vanishingly small probability of error. So if the code achieves a small probability of error with a bounded distance decoder, then it will also achieve a small probability of error with a minimum distance decoder. So I've specified everything except how do we choose the codebook. Now, designing the codebook is a very challenging task, and in particular, this was a long-standing open problem till very recently. So what Shannon did in his original paper, where he showed what the capacity of DMCs is, he didn't know how to choose a particular code. So what did he do? He just chose it randomly. So you choose each xn independently and uniformly at random. So choose each xn of I to be IID uniform over all possible binary sequences of length n. Okay, so each code word is chosen independently and uniformly at random. Okay, so this is how we are going to choose our codebook, and we will analyze the performance of this particular codebook with respect to bounded distance decoding over the BSC. Now note that this gives you a valid codebook, but encoding and decoding is not particularly efficient. In particular, the bounded distance decoding algorithm requires an exponential time complexity because you have to check all possible sequences. The time complexity of decoding is exponential in n, and so even storing the codebook requires a huge amount of space. You need to store 2 to the k possible sequences, each of length n. Right? So the total space required is n times 2 to the k minus 1. Sorry, n times 2 to the k, which is also exponential in n, since k is roughly n times r. Right? So this is not a very efficient encoder and decoder, and of course constructing the random codebook is also not very easy, because you need to sample 2 to the k possible sequences independently and uniformly at random. But this class of codes, this manner of choosing codes, encoders and decoders is easier to analyze, and that is indeed what we will do now. So in practice, we don't really generate codes at random, and we don't really use bounded distance decoding, at least for large block lengths. But this is a useful tool because it tells us how, it gives us some insights as to how we must design codes and how we must design encoders and decoders. So our goal is to minimize the average probability of error. right? So first let us look at the probability of error given that a particular message was transmitted. So for example, let's suppose that the message to be transmitted is the all zeros sequence. So message 0 needs to be transmitted. So the probability of error given that the 0th message was transmitted, so what is this equal to? So an error occurs if one of two things happen. Either the received sequence is far away from the transmitted sequence, that is, the received sequence yn is greater than a distance r from the transmitted sequence, or some other sequence, some other code word is close to the transmitted sequence. So here we are using a bounded distance decoder where r will be chosen to be np times 1 plus epsilon for some small epsilon greater than 0. Okay. So we're using a bounded distance decoder with a radius of a decoding radius r equal to np times 1 plus epsilon. So this is called the decoding radius. Now since the channel is basically yn equal to xn plus XORed with en, and en is IID Bernoulli P, we expect to see only roughly np once in en. So the distance between the transmitted sequence and the received sequence is going to be roughly np. Right? So that's why we add an additional tolerance factor of epsilon. So as long as the received sequence is within distance np times 1 plus epsilon, that we declare that to be the transmitted sequence. Okay, so this is what we have. Now the probability of error is basically an error occurs if either one of these two events occur, or in other words, it's a union of two error events. The first event is that the received sequence is far away from the transmitted sequence. The second event is that some other code word, a spurious code word, is close to the transmitted sequence, is close to the received sequence. So I'll use the union bound to write this as a sum of two things. So the first is that xn of 0 is far away from the received sequence, and the second is that some other message of some other code word lies close to the received sequence. So I've just used the union bound to decompose this as a sum of two probabilities. Now I'm going to use the union bound once again. So note that the second probability is actually a union of multiple events. So I can write this as a union So this is a union over all possible m tilde not equal to 0 of the event that the xn of m tilde lies within a distance of np times 1 plus epsilon to the received sequence, right? So again, using the union bound, this is less than or equal to the probability that the Hamming distance between xn of 0 by n is greater than np times 1 plus epsilon plus the sum overall m tilde not equal to 0 of the probability that dh of xn of m tilde yn is less than or equal to np times 1 plus epsilon. Now note that in this second term or in the second set of terms, yn is obtained by transmitting xn of 0 through the BSC, right? Whereas m tilde is not xn of 0, it is something else. Okay, so now if we want to show that the probability of error is small, then we have to show that each of these terms goes to 0, and it goes to 0 sufficiently fast. So let's look at the first type of error, which is the probability that the received sequence is far away from the transmitted sequence. Okay, so the probability that the Hamming distance between xn of 0 and yn is greater than np times 1 plus epsilon. Now this is easy to analyze, because this is the same as saying that the error vector has more than np times 1 plus epsilon number of ones. Okay, and this, just by using Chernoff bound, we know that this is less than or equal to e to the beta n, e to the minus beta n for some positive constant beta. So you can use Chernoff bound to find an exact value of beta. Okay, and this also, of course, this is beta n epsilon squared. It also depends on epsilon square in this particular fashion. Okay, so this is the first probability of error. So we know that the first term decays with n. Now we want to show that the second set of terms also vanishes with n. So let's look at the second type of error, and for this let us fix any m tilde which is not equal to 0. So in particular, let us say that that code word xn of 1 was transmitted. Sorry, xn of 1 is basically being considered. So let me denote pe of m tilde as the probability that xn of m tilde lies within a distance of np times 1 plus epsilon to the received sequence, when it was actually xn of m which was transmitted. So you transmit xn of m and get yn. So this is what the geometric picture looks like. So this is xn of m. You transmit this and you get a yn, and there is some other sequence xn of m tilde which lies within a distance of radius np to yn. Now in this case we don't really care whether xn of m is close to yn or not, because it will anyway lead to an error. So irrespective of whether the black dot is within the red ball or outside the red ball, we will still be in error because there is a wrong code word already within the ball. Right? So let's write this out in the following way. So this probability can be written as the sum over all possible yn, all possible received sequences, the probability that little yn is the received sequence, times the probability that a code word xn of m tilde lies within distance of np times 1 plus epsilon to yn. Note that xn of m tilde is independent of the transmitted code word yn. Why is that? That is true because the transmitted code word yn depends only on xn of 0, not on or it depends only on xn of m and not on xn of m tilde. Since we're generating the code words independently of each other, xn of m tilde is statistically independent of yn. Okay, so let us first see what this term becomes. Okay, so note that each xn of m tilde is generated uniformly at random. Right? It's uniformly chosen from the set of all binary sequences. So this is basically equal to, so this is the sum over all, let's say xn tilde, which is the sum over all xn tilde, such that the distance of xn tilde yn is less than or equal to np times 1 plus epsilon times the probability that xn of m tilde is equal to xn tilde. Right? So this is the probability that the random code word, so the code word corresponding to m tilde is actually equal to xn tilde. But since we're choosing each code word uniformly at random, the probability that xn of tilde m tilde is equal to xn tilde is always 1 over 2 to the n. Right? That is the probability that xn of m tilde is equal to any particular sequence, since it's uniformly distributed. So therefore this probability becomes 1 over 2 to the n times the number of sequences which lie within Hamming distance of np times 1 plus epsilon to yn. Right? And this, as we've seen previously, is 1 over 2 to the n times some constant times n times 2 to the n times the binary entropy of p times 1 plus epsilon. Right? Now that we have this, the probability PE of the probability of error of decoding as m tilde, given that m was transmitted, is the sum over all yn, the probability that you receive yn times 1 over 2 to the n times alpha n 2 to the n h of p times 1 plus epsilon. Right? Now this term over here is independent of yn, so I can take it outside, and the sum over all possible yn of pyn of yn is equal to 1. So this is basically 1 over 2 to the n, some constant times n, 2 to the n times the binary entropy of p times 1 plus epsilon. Which can be written in the following way. So it's alpha n divided by 2 raised to n times 1 minus the binary entropy of p into 1 plus epsilon. So this is the probability that the code word corresponding to m tilde lies close to the received sequence when the actual transmitted sequence is xn of m. So now that we have this, let's go back to what we had over here. So the overall probability of error, the average probability of error, is less than or equal to, the first term is the term corresponding to the first type of error, and that is vanishing with n. So it's e to the minus beta n epsilon squared plus the sum over all m tilde not equal to 0 of PE of m tilde, right? Now this, as we've seen, is, so this is e to the minus beta n epsilon square plus the sum over all m tilde not equal to 0 of alpha n divided by 2 to the n times 1 minus the binary entropy of P of 1 plus epsilon, P times 1 plus epsilon. Correct? Now all of these terms don't depend on m tilde, so I can just take it outside. So this is e to the minus beta n epsilon square plus alpha n divided by 2 to the n times 1 minus the binary entropy of P into 1 plus epsilon times the number of possible m tildes. There are 2 to the k minus 1 of them, right? But 2 to the k minus 1 is obviously less than or equal to 2 to the k, right? So it's 2 to the k, all right? But if I choose, so since r is equal to k divided by n, I can take k to be equal to nr, right? And if I choose r to be equal to 1 minus h2 of p times 1 plus epsilon minus epsilon, then the probability of error, the average probability of error, is basically e to the minus beta n epsilon square plus alpha n times 2 to the minus n epsilon, right? So if you plug it into the above equation, you get this particular quantity. So as long as I choose my rate to be equal to this, the overall probability of error is decaying with n. Note that this is alpha n times 2 to the minus n epsilon, and this quantity basically decays exponentially with n. So this is also vanishes. So this, in the limit as n tends to infinity, the probability of error is equal to 0. So it's the limit as n tends to infinity of e to the minus beta n epsilon square, which is 0, plus the limit as n tends to infinity of alpha n 2 to the minus n epsilon, which is also equal to 0. So what we've shown is that, since of course we chose the code book at random, so this means that there exists at least one code which achieves this particular probability of error and has this particular rate. So the rate that we can achieve is 1 minus h2 of p times 1 plus epsilon minus epsilon. Now epsilon is something that can be arbitrarily chosen. So what this implies is that any rate which satisfies r less than 1 minus h of p can be achieved. So any rate satisfying r less than 1 minus h of p can be achieved, which means that given any r which is less than 1 minus h of p, we can construct a sequence of code books. For large enough n, we can construct a code book such that the probability of error is vanishing with n and the rate is equal to r. Right? So right now we have shown that as long as r is an achievable rate, 1 minus h of p is an achievable rate for the BSC. Now later on in this course, we'll see that we cannot indeed achieve a rate above 1 minus h of p. That is, if we try to choose a code book whose rate is strictly greater than, let's say, greater than or equal to 1 minus h of p plus epsilon, or some small epsilon greater than 0, then the probability of error can never be made to go down to 0 as n tends to infinity. So for large enough n, every code book which has a rate greater than 1 minus h of p cannot achieve a vanishingly small probability of error, cannot achieve a small probability of error. So this 1 minus h of p is a fundamental limit on the rate, on the achievable rate for a binary symmetric channel.